Today we're going to talk about a very specialized sort of regression analysis referred to as stepwise regression. Stepwise regression has a number of applications. It's either a nice system to use when you have very large data sets and a very large number of predictor variables, and or it's valuable when you have a relatively small data set with lots of predictor variables. In either case, what you're trying to do is build a predictive model which is as parsimonious as you can possibly get it. In the case of a data set in which you have very few observations, the reason you'd like a parsimonious model is because you're limited by degrees of freedom. Recall that we would like to have, if the data are perfectly normally distributed, a minimum of 10 observations per parameter that we're trying to estimate. And ideally, we'd like to have 30. So if you have a small data set and lots of predictor variables, you'd like to estimate the fewest number of parameters possible. And in so doing, improve the robustness of your estimation effort. The data set that I'm going to talk about is one that I collected back in the 1970s. I was working on a project trying to understand the patterns of species diversity in lizard communities in the southwestern United States. And it involved an awful lot of field work. There were visits to each field site took about 4 days, and you had to travel to the field site, and then you spend 3 days sampling the field site and then move on to the next field site. And the way the sampling would work is you would arrive at the field site, and after you'd set up camp, you would go out and start walking and looking for lizards. Any lizards that were observed were collected and then identified to species. And then for each individual captured, there were many variables that were recorded in terms of various habitat parameters, ambient temperature, perch temperature, height above the ground for the perch, and so on. So there was a lot of time involved with each specimen captured. So for each study site then, and you can see that in the table that's presented right here, for each study site there were a certain number of species, the kind of habitat, which is a binomial variable, and that was whether it was an open habitat or a closed habitat. So desert or grassland or sagebrush scrub, something of that sort, versus a woodland, either a pinyon juniper woodland or perhaps even a ponderosa pine woodland. And then, in addition to that, there were many variables that were obtained from weather stations that were nearby. And the values that you see listed across the top of this table are for 30 years worth of data. So these are the averages over 30 years, the 30 years preceding the field season. So these are mean January temperatures, mean July temperatures, number of frost-free days, which is typically used as an indicator of the length of the growing season, the amount of warm season precipitation, the amount of cold season precipitation, and then the coefficient of variation of precipitation, which was used as a sort of an index of climatic stability at that particular site. There was a seasonality index, which was derived from the autocorrelations, which we've not yet talked about. But it too is an indicator that the larger the number, the more seasonal that particular site is. A spatial diversity index, which was a really lengthy sort of process, but looking at all of these covers, relative frequency, relative cover, relative dominance indices for all these different plant species. And then computing this value based on that. And then also latitude and altitude. That should really be elevation, not altitude, but that's a fine point. So latitude, because as the farther north you travel, obviously, the fewer possible lizard species you imagine there will be. And then elevation, obviously as you move up in elevation, the vegetation changes quite dramatically, but also thermal regimes change quite dramatically, and you can imagine that for lizards, temperature is going to be important. So these are the data, and what I would like to point out is that um, there are, well, this is now the incorrect data set. There are 20 study sites. On this table, there are only 19. I will fix that. There are 20 study sites, so this is a relatively small data set. This is a year, well, a full summer plus some worth of field work, being constantly in the field. So it's an awful lot of effort goes into getting a relatively small array of data here. So we're trying to predict species diversity, the number of species here. I shouldn't say diversity, I should say species richness. We're trying to predict the species richness based on all of these variables over here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 variables. So if the data were perfectly normally distributed, then we would need at least 110 observations or 110 study sites, and we don't have that. If the data are not normally distributed, then we would need 3 times that number. So you're looking at 300 or 400 observations, and that clearly is not within the realms of possibilities for this kind of a project. So now we're faced with this issue. How are we going to analyze these data? How are we going to build a predictive model with this handful of observations? All right, so we can do it. The technique that we're going to use is referred to as a stepwise regression analysis. And it, as the name implies, it happens one step at a time. So there are a number of ways that we can do this. There are, if you were to go through SAS, which is the ideal package to do this kind of work, you would have a number of ways to approach it. It's a bit more limited in R, but there are 4 basic approaches. The first approach is referred to as a maximum R-square improvement technique. And what happens in max R, as it's referred to, is that you begin with a model that has no predictor variables in it, and then you add a variable into the model and compute all of the relevant statistics. And the most important one in this technique is the coefficient of determination, the R-square. And you search for the single variable which has the largest R-square. And once you find it, you include that variable in the model and you throw everything else out. So you now have the best possible one variable model, and you've chosen that variable on the basis of R-square. Once you have that best one variable model, you then attempt to add a second predictive variable. And again, you're looking for the variable that provides the best improvement in the R-square and the coefficient of determination. And you continue with that until you've added all of the variables into the model. So in this situation, we have we have 11 variables, so you would end up with a model that has 11 variables in it. And of course, you would have an R-square that would be pretty close to perfect, right? The R-square would be very large. The more variables you add into the model, the higher the R-square is going to be, so it gives you a false sense of security. It is important to point out, too, that there will be lots of collinearities amongst these variables. So it's probable that January temperature and frost-free days are going to be correlated, and or that the seasonality index and coefficient of variation of precipitation will be correlated, and so on. So all of these variables are collinear. So none of these things are orthogonal. None of them are statistically independent from one another. And that then is going to introduce all sorts of bias into our model. So we have to have some sort of way of protecting ourselves against that kind of bias, at being able to identify it. And there is another issue that presents itself as well, and that has to do with how we're computing the sums of squares. Now, our method of computing sums of squares, up to this point, we've been using what's referred to as the type 1 sums of squares. And the type 1 sums of squares assumes that the design is balanced and assumes that there are no collinearities amongst the variables. We don't have that here. And why is that important? That's important because with the type 1 sum of squares, if you change the sequence of the variables in your model statement, then the sums of squares will be different. So order is important. If you have a situation where you have collinearities and where you don't have a balanced design, your sums of squares are going to change dependent on the order that you place them in the model statement. So we need some way to escape that, and the way we're going to escape that is by using a type 2 sums of squares. And what a type 2 sums of squares is a conditional sums of squares. So it's giving you the sum of squares for your particular variable, the one that it's evaluating in that step, conditional on the presence of all other variables in the model. So it's giving you a less biased perspective on what is going on with your model. So that's the first thing we'll do. Instead of using a type 1 sum of squares, we'll use a type 2 sums of squares. Type 3 sum of squares is also a conditional sum of squares, but it's not appropriate in this particular circumstance. So now the next thing that we need to concern ourselves with is the potential bias that's going to be inherent in the model. And what we've been doing up to this point is just talking about the coefficient of determination. There is another parameter that we can look at which will help us assess bias, and that is Mallow's P statistic. That's denoted usually with a capital C and then a subscripted P. And Mallow's P statistic is an indicator of bias, and it increases isometrically with the number of parameters that are in the model. So if you have 3 parameters in the model, then the ideal Mallow's P would be 3. If you have 4 parameters in the model, or 4 variables in your model, then Mallow's P statistic in an unbiased model would be 4. As you introduce variables into the model, Mallow's P statistic is going to get smaller. So if you have 11 potential variables that can fit into your model, as we do here, and you introduce the first variable, Mallow's P statistic is likely going to be very large. So it may be 7 or 8 or 12 or something of that sort. And now, as you add a second variable into the model, Mallow's P statistic is going to decrease rather dramatically, and it's going to come closer to your line of isometry. And at some point, it's going to cross that line of isometry and drop below it. If that happens, you've gone too far. The ideal number of parameters that you have in your model is going to be one in which Mallow's P statistic has come as close to that line of isometry as possible without dipping below it. Now, unfortunately, in R, there is no intuitively obvious way, to me, at least at this point, of how to extract Mallow's P statistic. Instead, what R does is it uses something referred to as a Keiki's information criterion. That's usually referred to as the AIC value. And that is an attempt to do 2 things. A Keiki's information criterion is an attempt to summarize both the coefficient of determination and Mallow's P into a single metric. The difficulty with the AIC is that the value itself really doesn't give you a lot of information because it's going to be dependent on the nature of the data and all of those sorts of things. So it's not possible to compare an AIC value from one study with an AIC value from a different study. Now the solution that most people use around that is within a particular study they compare one model with another model based on something referred to as the delta AIC. That is, how much did AIC change from one model to the next? And their objective is to get the model that has the smallest delta AIC. We're not going to delve into AIC, but as a biologist, you should just prepare yourself for the fact that you will encounter that frequently in the future. All right, so we've now talked about our first possible approach to building a model, and that is the forward selection routine. There is an alternative, and that's referred to as the backward selection routine. And in a backward selection routine, what you do is you attempt to remove variables from the model one at a time. So you begin with all variables in the model at once, and then progressively attempt to remove the variable which has the least effect on the model. And you can do that using something called a minimum R-square improvement technique. So instead of trying to maximize the R-square, you can try and minimize the R-square, the change in the R-square. Alternatively, you could begin with no variables in the model and attempt to add variables to the model one at a time using minimum R-square. And in so doing, the idea is that you'll get to some point where by constructing the model in this way, you will have somehow reduced the amount of bias. Now, how do you decide which model is best? Well, again, there are two criteria. What is Mallow's p-statistic, and what is the ultimate coefficient of determination? There is something else that's important to look at, and that is, what are the p-values for the variables that are in the model? The way typically that this is evaluated is by deciding a priori what the critical values are for the p-values that you're going to put into this model. The default is usually to use a p-value of 0.15. That is, you're going to attempt to add a variable into the model as long as its initial p-value is 0.15 or smaller. If the p-value is larger than 0.15, you're going to ignore it and move on to the next variable. Now, once that variable is in the model, the p-values for all of the other variables are going to change. But as a default, you're going to not even look at the variable unless it has a significance level to enter the model of at least 0.15. You can also flip that around a little bit and say, okay, once variables are in the model, we may decide to remove variables from the model, and there we'll use a significance level to stay in the model as something. And again, the default is usually 0.15. Now, if you have a really large data set and lots of variables, and you really want the most parsimonious model possible, what you can do is tighten up those significance levels for entry into the model and to stay in the model, and you can drop them to 0.1 or 0.06 or whatever you'd like, and that will simplify your life rather dramatically. But it does make an important point, and that is that this whole model building process, there is no magic bullet. You can't simply turn on the computer and ask it to give you the absolute best model, because it has no idea. The best model is going to be a function of what you need, what you're looking for, what you're willing to accept, and what you're willing to tolerate. So this is the sort of exercise which is going to be dependent on your experience and your knowledge of the system. So we've now talked about maximum R-square improvement. We've talked about minimum R-square improvement. We've touched on backward elimination, that is, beginning with all variables in the model and then attempting to remove them one at a time, again looking at the R-square and looking at Mallow's P. And then the final approach that's used in SAS is what's referred to as a forward selection routine, where you attempt to add models one at a time, as in the max-R improvement technique. But now when you're adding them one at a time, you can look at a host of different values, right? You can look at Mallow's P, you can look at the R-square, you can look at those sorts of things. You can adjust the significance level to enter and the significance level to stay and so on. But what will happen in all of these techniques is you will end up with a long list of potential models. And once you have those potential models, it's then your job to select which one works best for you. Well, there is where we need to think a little bit about exactly where our cutoff point is, because here we have 11 variables. And if we go through any of these, the final model is either going to have nothing in it or it's going to have 11 variables in it, and we don't want that. So we have to decide which model out of all of those possible models is the one that we're going to select. What you can do is you can make yourself a little graph. On the x-axis you can have the number of variables in the model, and on the y-axis you can put the R-square and look at the best one variable model and plot what the R-square is for the best one variable model, and then plot the R-square for the best two variable model, and so on. And what you'll see then is that the R-square increases pretty quickly at first and then begins to asymptote out. Obviously it can't be larger than 1. So you can look at that curve and say, well, I get the most bang for my buck when the model has 2 or 3 or 4 variables in it, and beyond that point the R-square really doesn't change very much. So that's one criterion that you can use. And then you can also look at Mallow's P and say, well, you know, if I have 2 variables in the model, then I'm still unbiased, but if I have 3, then suddenly I have a fair bit of bias introduced into the model. So you might then decide to stick with the 2 variable model. But it is an exercise which depends on your experience and your knowledge of the system. All right, so what I'd like to do now is use these data to build a stepwise model using R. And this is a little bit complex now. It's not as one step easy as it was in some of the other techniques that we've used. So what we're going to do now is open up R and build our model using R. And we're going to use sort of an amalgamation of the different techniques. And we're going to use a sort of a stepwise function which is going to leap backwards and forwards, and it's going to attempt a host of different techniques to arrive at the best model. And I think what you'll see is that it comes reasonably close to what SAS would have done for us. I've obviously run these data with SAS many times, so I have a certain expectation of what we should be getting, and it turns out that R does reasonably well in coming close to what SAS would do for us. So let's begin then with that. So here I've opened up R, and let me resize this a little bit so I can see. I've already put together the commands that we're going to need over here on the right, which these will be available if they're not already. I can't recall. The data set is already available on the website, and I will get these commands up as well. So let's start by using some of these commands. The first thing that I'm going to do is rm list equals ls. There we go. So we've cleared the data set. And now what I need to do is enter the data from the computer. So I need to type in the read.csv command to get the data set. Alright, so let's continue on. I've repaired the data set with regards to both the variable name and picking up that missing row of data, and we're now ready to load up the next variable. So what I'm going to do, I'm just going to go over here and copy this command and then bring that over here to our, and then Control V, there we go, and now hit enter, and now I have my dialog box which is opened, and I put that on the desktop. There we go, lizard ecology, and now the data you can see up here in the on the global environment that the data are there. Okay, very good. So now there are a number of things that we need to do. Let's just make sure that the data are appropriate. So I'm just going to type in Liz Eco. That stands for Liz Ecology or Lizard Ecology. And there it is. Looks like everything is there. Yeah, so I've added this first row. So now we have 20 field sites. Actually, there was a 21st field site, which was an absolute total bust. I'd gotten to that field site and had been through many museum records looking for exactly what I wanted in terms of species and abundance and whatnot. And when I got there, it had been overgrazed in the subsequent years, in the subsequent 100 years or so, and there was absolutely nothing left. All right, so now I'm just going to type in attach. So we've now attached the data set, and now there are a couple of things that we need to do. We need to add some packages. What you'll have to do is you're going to have to go through your packages right here, click on this, and make sure that you have the following packages. If you don't have them, you're going to have to install them, and that's relatively straightforward to do. You can just click on the install command here and type in the name of the package that you need, and R will go through all of the work of installing that package. So the packages that we want are a package called Carrot, Leaps, and Mass. Okay, so note Mass is M-A-S-S, capital M, capital A, capital S, capital S. Carrot and Leaps are a little bit different. They're all lowercase. All right, so I've already gone through all that work, so I'm just going to call up library Carrot. All right, so now you can see that it's loaded that. I'm going to load library Leaps. Okay, and it gives me a warning that Leaps was built under an older version of R, which is fine. And then library Mass. Okay, so we are good to go. And now what I'm going to do is set a random number seed. So set .seed. And we can use anything. I'll just use 1, 2, 3. Okay, so now it's set the seed for us. And now I need to go through a number of steps here, and I'll explain these in just a moment. Okay, so the command that we've just introduced, this train control, I'm assigning the results of this to a new variable called train control. So train.control is actually a function in R, and it's essentially a set of instructions to R to search for a particular parameter. So I'm going to use a method called cross-validation, hence the method equals CV, and then I'm also using this number equals 10, so I'm going to do this over a 10-fold series of trials. So it's a cross-validation routine, and all I'm doing is I'm trying to tune the model to the best possible parameter estimate. The next thing that I'm doing is I'm using a stepwise model, and that's indicated here in this next variable. So stepwise model, and let's see if I can get this thing. Yep. Let's go down here like this. There we go. So I'm now going to use this particular command, and I'm just indicating to R that we're going to do this in a stepwise function. So here, what we're doing, we're going to assign, we're going to build this model, and the dependent variable in the model is species. So that's the number of species at each study site, so species as a function of, and then I use dot. And what that does is it tells R that it's going to use all of the variables in the data set. If there are some variables that I don't want to use, perhaps some are variables that simply don't belong in there or whatever, I can indicate which columns of data that I want to use. But we're using all of them, so that's all we need. So I specify the data. Method is leap backwards. Okay, so I'm going to try and go back. So I'm going to enter variables in and then leap backwards. In other words, I'm going to try a backward elimination routine. And then I'm going to specify the data frame and the number of variables maximum in the data set in the model is going to be anything between 1 and 5. So I'm already indicating from the beginning that I don't want to look at any models that have more than one variable in them, and I don't want to look at any models that have fewer than one variable in them. Right, and then my train control is equal to train control. So that's just this setup of the sequences that I need to run this particular model. Okay. So now let's go ahead and look at that first group of results. So I have step model results, and let's see what that looks like. And here you can see I get a number of sort of worrisome results, but interesting just the same. So the number of variables max on the left-hand side, it's 1 through 5, and it gives me then the regression mean squared error, and it gives me the R square, and you'll notice that the R square is 1 in each case. So I'm getting a total explanation of what's going on in each of these cases, and that obviously is not helpful, because that obviously means that the model is over-described. Right, there's nothing left, and you can see that in the R squared standard deviation that it's basically 0. All right, so here's the regression model squared error. Right, that's all fine and dandy. Okay, it's just not exactly what we would like. So now let's look at this model, the best tune. All right, so I'm going to add that command in there. Right, and it tells me that the best model is going to have three parameters in it. Fine. I probably won't go that far. Let's do the next one. Let's look at the summary of this particular model, the summary for the final model. Let's put that command in there. And now this is sort of an odd display, but let's go through it and see what it's telling us. So here now it's giving us the 1, 2, and 3 variable model, and then across the top here it's listing the different variables that we're introducing. So it's broken up into two groups. I suppose if I made this bigger it would stretch out a little bit, and I can't see it in my display here. No, it doesn't, so that's fine. Let's go back to where we were. Let's go through these. Notice that it's just a bunch of quotation marks, but here in this first, the best one variable model includes January temperature, okay, and that's the only thing that shows up. So that right away tells you that January temperature is one of the variables that will perhaps be important. The best two variable model has January temperature and WSP, which is warm season precipitation, and then nothing else. The best three variable model has January temperature, July temperature, and warm season precipitation. So from an ecological perspective, this is beginning to make a little bit of sense. If you're thinking about what it means to be a lizard, especially in the Southwest, January temperature is going to be important, because the colder it is in January, that probably means the shorter the growing season, and that's not good for a lizard. July temperature is important. Lizards obviously like warm places, right, but not too hot. And then warm season precipitation may be important because it might be related to productivity, and of course the more productivity, the more insects, but also the more productivity, the more shade, and lizards aren't real big fans of shade, at least not out in the desert. So now let's go ahead and look at what the coefficients are, and we're going to do that. So this has just told us so far what variables are in the model, but we have no idea what the model really looks like. So what we're doing is we're going to look at the final model that contains two variables, and here we get it. So the best two variable model has an intercept, fine. January temperature, notice that the number of lizard species is positively related to January temperature, which makes sense. The warmer it is in January, probably the longer the growing season, and probably the warmer it is in the summer. And then negatively associated with warm season precipitation, that is, the more rainfall there is in the summer, the fewer lizard species. Well, that's probably because areas with more rainfall have more trees or more vegetation, which means there are less opportunities for basking from the perspective of the lizard. So now let's go another step here, and we're going to use a different technique. So that was a sort of a leap backwards technique. Now we're going to use a leap sequential. This is equivalent to the default stepwise technique that's used in SAS. So that's where it's a combination of backwards and forwards elimination, and we're going to look at the best two variable model. So it has some resampling, missing values. All right, we're not going to worry about that. And now let's, here's again the summary that we had before. The R-squared is again 1, which clearly is not ideal, right? But we can see this basic overall assessment of what's happening with the ability of the model to predict what's going on. So now let's look at the best two variable model. Whoops, the best model. So I have step model 2, step model 1, and so on. So the best model is again a 3 variable model. And if you stop and think about it, I really don't want a 3 variable model because I have 20 sites. If I use 2 variables, that means I still have or I have 10 parameters or 10 variables, 10 observations per parameter being estimated, which gives me sort of a leeway in terms of minimizing bias. So here, let's look if we end up with basically the same thing. Looks like it's a little bit different. In each case, January temperature is included. The best two variable model has January temperature and spatial diversity. The best three variable model has January temperature, July temperature, and warm season precipitation, just as we had before. All right. All right, let's look at what the coefficients are there. Let's see, where am I? Summary, step model 2. Summary, step model 2. Final model. And let's look at the coefficients. There we go. And let's see, we have here, it's still positive, right? We had a positive relationship up above. Here in this approach, the coefficient is 0.1267. Let's see what it was before. Here it was 0.088. So that relationship has changed. Again, remember, these are conditional. And here, as spatial diversity increases, number of lizards decreases. All right. Let's look at the coefficients for the three variable model. And see what we get there. So January temperature is positive, just as it was before. July temperature is negative, and now notice that we have warm season precipitation, and that's negative. So the question now becomes, which one of these models that we've looked at is the best model to explain what's happening in this system? I can tell you that the model that I chose when I published this work was basically this third model right here. I would have preferred a two variable model simply because that gives me then 10 observations for each parameter. But it was missing, that best two variable model was involving spatial diversity and January temperature. And in terms of understanding what was going on with the lizards, January temperature, July temperature, and warm season precipitation make the most sense and are the easiest to explain. So now I'm in a position where I have basically 6.5, 7 observations per parameter that I'm trying to estimate. And the justification that I used for the editors was that I really didn't care what the exact values of the coefficients were, merely whether they were positive and or negative. And the other point that I made in justifying this particular model was that this model explains about 75% of the variation in the data. So January temperature, July temperature, and warm season precipitation explain roughly 3/4 of the variability in species abundance patterns that we see in the desert Southwest. And the reason that was important in this paper was because at the time there were lots of arguments about the importance of interspecific competition and predation and those sorts of things. And in this paper I was simply making the point that really more important than all of that stuff is this concept of productivity and temperature, and that you didn't need to use competition or any sorts of more complex kinds of phenomena to explain what was going on. All right, the next step in all of this would be graphical, and that is to make a series of plots or whatever that would show what was going on. This gives you the ability to do a stepwise multiple regression. It's kind of clunky compared to SAS, and it doesn't give you everything that you would like. In order to get the R-squares and so on, you have to work a little bit harder. In order to figure out what the bias is, you have to work a little bit harder. All of those sorts of things. So it isn't quite as nice as SAS, but it is functional, and R is free. So that's it for stepwise regression, or at least this first shot at stepwise regression, and we'll do more later. Good deal. Talk to you guys later.